Let's look at marginal and conditional distributions. Now, marginal distributions turn your two-way table back into a frequency chart by ignoring one of the variables. So if we're looking at the distribution of colors, then we could care less what type of animal we have. We basically want to ignore the type of animal and the breakdown from that. So let's ignore those parts of the table and only look at this one margin. So the distribution of colors, the marginal distribution, would be 128 one-color animals, 78 two-color animals, and 26 animals with 3 or more colors. Same idea applies in the other direction. The distribution of animals doesn't care anything about the color. So we can completely ignore the information about how many colors each animal is. What we care about is the total number of cats, total number of dogs, and total number of animals in this margin, the right margin here. So depending on which distribution you want to see, you get to ignore the other variable when you're finding marginal distributions. Conditional distributions are very much on a similar wavelength, but a little bit different. If you're looking for the distribution of one-color animals, that means that you are not interested in two-color animals, or 3+ color animals, or animals of all of those mixed together. You only care about one-color animal. So your one-color animals would be the distribution of this many dogs, this many cats, out of this many total. Moving on, distribution of colors of dogs would only look at dogs. So we would look at just the dogs. We would ignore everything from the cats. We would ignore everything from the total number of animals. And what we're doing here is, again, we're taking, just like in the marginal distributions, we're taking a single row or a single column, but instead of using the margin, we're going to use one of the main rows or main columns. Last thing is graphing a conditional distribution. If you have a distribution like we have here, and you want to know the distribution of cat colors, let's go ahead and use our red pen for cat colors. We have 53 one-color, 45 two-color, 14 3 or more color cats. And if we were to throw this on a graph here, we would label our axes. And over here we would have number of animals. And the reason I'm going to use animals is because dogs will eventually end up on here too. So number of animals. Otherwise we could just do number of cats. And we are going to graph a bar for each of these. So we have one color, and we'll make a bar of height 53. Two color, and you make a bar of 45. And again, when we're making these, I'm not going to be super picky about them being perfect, but they should be clearly representative of the rough size so that you can see what the graph is basically about. So we'll have 3+ color over here. And this is distribution of cats. Now if you want to do distribution of dogs and you did that in a different color, if you have only a pencil, you'd probably want to shade it differently or do something to make it clear which one is which. But you're going to look at your dog distribution here. 75 of one color, 33 of two colors, 12 of 3 or more colors. And since it's a bar graph, you're usually not going to have your bars touching, unlike you would in a histogram. And the reason you would make a graph something like this out of a two-way table is because in the table it's a little bit hard to see the general relationships of things and how they all compare overall. But here it's a little bit easier to say, oh wow, when it comes to dogs, it seems like there's more one-color dogs than cats, but there's fewer two-color dogs than cats, given that there's roughly the same amount of each. In certain situations, if you have, let's say, way more dogs than cats, you might want to graph percentages instead of the actual counts from the table. So sometimes graphing these as a percent from the conditional distribution will work a little bit better.